In 1942, Nazi Germany needed a long-range heavy bomber capable of striking deep into British and Soviet industrial targets. The answer was Heinkel He 177 Greif. On paper, it was formidable, the only heavy bomber Germany produced in significant numbers. But the engineering decision was flawed. To reduce drag, engineers coupled two engines into a single nacelle, driving one propeller. This created a mechanical system that was extremely complex and highly unstable. The engines overheated constantly, leaked oil onto hot exhaust components, and frequently caught fire mid-flight. Crews gave it a nickname, the Reichsleiter. Over 1,000 were built. Yet operational reliability was so poor, it was effectively useless as a strategic bomber. Germany then pushed technological limits with the Messerschmitt Me-163 Komet, a rocket-powered interceptor capable of reaching nearly 600 miles per hour, faster than anything the Allies could deploy. But the engine burned for approximately 8 minutes. After that, the aircraft became a glider, unpowered, unable to maneuver effectively, and unable to evade enemy fighters. It became a slow, predictable target. The fuel system introduced an even greater danger. Its highly reactive chemicals could ignite on impact, often killing pilots even after survivable crashes. Of the roughly 300 aircraft built, more were lost to accidents than to enemy action. As the war situation deteriorated, Germany needed fighters faster than it could train pilots. The result was the Heinkel He 162 Salamander, designed to be built in just 69 days, using non-strategic materials, primarily wood. But the construction introduced critical weaknesses. The adhesive used in the wooden structure degraded in moisture, causing structural failures during flight. The engine was mounted directly behind the pilot's head. When engine failure occurred, debris often struck the tail section, making recovery impossible. Experienced pilots considered it dangerous. The minimally trained pilots assigned to it had almost no chance. Japan faced a different limitation: industrial capability. Their response was the Nakajima Kika, inspired by German jet technology. But the engines produced only about half the thrust of German equivalents. The first flight in August 1945 succeeded. The second attempt failed to take off properly. 6 days later, Japan surrendered. The aircraft never reached operational status. The Kyushu J-7W Shinden represented one of the most radical interceptor designs of the war, a canard configuration with forward wings and a rear-mounted propeller. It was designed to climb rapidly and intercept B-29 bombers. The aerodynamic concept was innovative, but early test flights revealed stability concerns. Only 3 flights were completed before the war ended. Whether it would have worked in combat remains unknown. Not all failures came from poor engineering. The Northrop YB-35 flying wing was aerodynamically efficient, a single large lifting surface carrying crew, engines, and weapons internally. The design reduced drag and improved efficiency, but without modern flight control systems, it lacked stability. Pilots reported constant oscillations, requiring continuous correction. The concept was correct. The control technology did not yet exist. The McDonnell F-85 Goblin attempted to solve a real strategic problem. Long-range bombers needed fighter escort, but fighters lacked the range. The solution: a parasite fighter carried inside a bomber. It would deploy mid-air, engage enemy aircraft, then dock back onto a moving trapeze. In testing, docking failed more than 90% of the time. Even under controlled conditions, the maneuver proved extremely difficult. In combat, it would have been nearly impossible. The Convair F2YC Dart was designed to eliminate the need for runways, a supersonic seaplane capable of operating from water. It used hydro skis for takeoff and landing, but at high speeds, those skis transmitted severe vibrations through the airframe. The vibration problem was never solved. In 1954, during a public demonstration, the aircraft disintegrated mid-air. The program was cancelled shortly after. The British Miles M52 aimed to develop the world's first aircraft capable of breaking the sound barrier. It featured a straight-wing jet design and an advanced all-moving tailplane. Modern analysis suggests the design would have worked, but the program was cancelled in 1946, officially for safety reasons. Before cancellation, key research data was shared with the United States. That data later contributed to supersonic flight achievements. The Vought-X F7U Flying Flapjack was one of the most unconventional aircraft ever built, a disc-shaped design with propellers mounted on the leading edge. Wind tunnel tests showed exceptional low-speed lift and promising high-speed performance. A prototype was completed, but rapid advancements in jet technology made it obsolete before full deployment. The Convair XFY Pogo explored vertical takeoff and landing. It launched vertically from its tail, then transitioned into forward flight. But landing required the pilot to reverse the process while looking over their shoulder. On a moving ship deck, this demanded extreme precision. Test pilots proved it was possible, but not practical for operational use. The Ryan XY-5 Vertifon used lift fans powered by redirected engine thrust. The design eliminated exposed rotors, but it introduced a new problem. The powerful downward airflow created a ground vortex, pulling debris into the fans. This caused severe damage and fatal accidents during testing. The F7U Cutlass represented a futuristic naval fighter design, a tailless, swept-wing aircraft intended for carrier operations. But its engines produced insufficient thrust, especially at low speeds. Landing required a high nose angle, reducing pilot visibility. Hydraulic failures were common. Approximately 25% of all aircraft built were lost in accidents. The Republic XF-84H Thunderscreech attempted to combine turboprop efficiency with jet-level performance. Its propeller operated at supersonic speeds. This generated continuous shock waves, radiating from the blades. Ground crews reported nausea, disorientation, and even seizures. The aircraft became one of the loudest ever built. Finally, the Bell X-22 explored tilt-duct propulsion. It successfully demonstrated vertical takeoff using rotating ducted fans, but controlling the aircraft required constant pilot input. The system was too complex for reliable operational use. These aircraft shared a common truth. On paper, they were revolutionary, but in reality, they exposed the limits of engineering, technology, and human capability. Because in aviation history, innovation alone is not enough. Execution is everything.